Hello. Today we'll be just starting from where we have actually left yesterday. So yeah, so we were defining what is say. It is basically we were talking about a pseudo inverse. So I'll just give a quick overview what we actually discussed last lecture. So what we were discussing was, suppose there is any vector, let's say 1, 2, 3, right? Whenever any vector is defined, we have something known as a reference coordinate system and check always along with it. Okay, because any vector into a reference coordinate system it will give you the same vector itself. Correct. Just writing it this side so that the dimensions actually match. So what is this doing? So what we discussed earlier is that this is basically a direction, right? So this is a direction, and this is any vector can be defined as a scaling factor to the direction. So in that manner, so let's say the direction is 1, 0, 1. That is, this is three dimension, right? So we have directions along x-axis, y-axis, and z-axis, which is shown here. And 1, 2, 3. Scale the x-axis by 1, 2, and 3. So it will be like it will come out of the paper 3. I think you almost understand where that point is. This is what we were discussing when we simply defined a vector, right? Now, that is for the standard coordinate system. So every vector, when written simply, is with respect to a standard coordinate system. But now, in the case when we do a, let's say, 1, 2, 3, 4, 5, 6, 8, 9, 11, whatever. Okay, so in the case when we actually define a vector in this way, what does this mean? This means that with respect to the standard coordinate system, you take this vector 158. So with respect to the standard coordinate system, suppose we have a vector. Uh, do cope up with my drawing as I mentioned before. So we have a particular vector, let's say 158. It will be somewhere. It is coming out of the paper, but okay, I can only draw in two dimensions. I hope you understand. 158 will be a vector which is coming from origin to that point 15. Likewise, we'll have another vector to something like this or this. So, which for the ease of representation, I'm just removing the standard coordinate system and just drawing the vectors. So, it'll be something like any vectors, any three vectors in a matrix. When you do a matrix multiplication with a vector, other than the unitary matrix, what we are actually doing is you have, let's say, any three vectors. Not these numbers, I'm just writing three random. Let us say it's A, B, and C. Okay, so suppose we have those sort of vectors, we have three vectors in any direction. So what we are doing is having this vector in the standard coordinate system. You do one thing, you scale A by 1. Let's say A, B, C. You scale A by a factor 1, scale B by, and obviously, vector addition. This will come here. B vector, you scale it by, I mean, you need to translate it, right? By adding two vectors. B vector, you scale by 2 and add to it. And the C vector, you scale by 3 and add to it. So what will be the resultant from here, right? This should be the origin of the coordinate system actually. So this is what actually basically you're just giving that now you don't have a standard coordinate system. You have what you say, you have a directions. You have three directions, and how much should I scale this direction to reach a particular point? That is what is actually coming out by a normal matrix multiplication, right? So normal matrix multiplication is nothing but telling us that a collection, stacked collection of vectors, how much we want to scale it so that we reach a particular point. Now, that same notion, let's say you have a vector. I'm not drawing the full vector space this time. A, B, C. and you multiply it by x, which is again another vector. You will get a again another vector, that is y. This means that x, each what you tell, each dimension of x, that value, if you scale the using that value, if you scale these three, you'll reach a point y, right? Now inverse of a matrix is nothing but from y, what direction set. Y will also be having some scaling factors. Some, let's say m, n, l, something, right? That will be y, right? So y will also be having some sort of scaling factors, and you need to now the inverse of this matrix is nothing but, can you give me a vector? I mean, I mean a direction if scaled will get me back to x in the standard coordinate system. Y is, suppose y is in the standard coordinate system. Can you give me some directions which, if scaled and I travel, I'll reach back to x? That is what you mean by the inverse of this matrix. Let's say this matrix is capital A. That is what you mean by let's say A inverse, right? So you want a direction. So obviously when you need and yesterday, I mean last lecture we have also just mentioned that this A vector, if it doesn't see what you tell, the point y is like the A vector has, let's say, independent has what you tell, dependent vectors. A and B are dependent. It may not be able to always reach a third dimension, right? Right. So in that case, how do you, I mean, suppose A, I mean, then you cannot actually return, right? The return path, uh, and there might be a case, the return path is not defined. That is when the inverse is not defined actually. I mean, there will be no vector through which you can actually, I mean, just come back here, right? So that can happen due to a few reasons, right? Because suppose A, the direction set A has some directions which cannot be traced back, right? Scaled back, right? In those cases, you will find a way where, I mean, you won't have an inverse for a particular matrix. There is no particular matrix which scaled will get you back to this point, right? So those concepts we have actually discussed. Now, having said that, also yesterday I think we did also mention, so we can't see, there is a schoolboy and his home, he has some directions, he just has some scaling factors, and he uses a direction set, and he'll mention like what direction, how he should scale each direction to reach his home. Suppose that schoolboy only has that direction set with him, and an army man has a separate direction set, he can do an airlift, right? Then obviously I told that the schoolboy can only reach as good as h bar, I mean underneath the helicopter point, right? He cannot, he doesn't have a direction set to reach there. So I mean, so the schoolboy doesn't have, what you tell, it cannot be inverted. That's the way we push it, right? A army man's direction set led him to h, and from there, schoolboy using his direction sets cannot come back, right? That's when I told there is no inverse for this guy. So what he can get is maximum get using his dimensions, maximum get underneath this, right? So that is what is known as a pseudo inverse. I think I did not define this specifically last time. Pseudo inverse, right? This concept is used in PC algorithm also, but overall, that is what we define by a pseudo inverse, right? I mean, what is the closest, using my direction set, what is the closest I can get to that, right? So that is what we call as a pseudo inverse. Okay, this much concepts we have just seen. Now we look at some other interesting concepts where, what you tell, what is a matrix doing? What is when you travel through certain directions, scale directions, right? You have a particular, let's say, A, B, C. You are a vector, three-dimensional vector with these values, and you travel through certain, say, directions. Let's call it L, M, and N vectors. You travel a times through L and b times through M and c times to N, and you reach what happened? You reach some other point. Obviously, you will reach some other point. Let's say X, Y, Z. Okay. Now the question arises: what happens to ABC? This is when you look at it from a direction perspective. But if you start looking it from the this and this, all of them, if you start looking from a standard coordinate system, right? Then the question comes, what is this matrix doing to A, right? So that is very quite an interesting question, right? What this matrix can actually do to A. See that question in we will take a very simple example and actually address that question. What is this matrix actually doing to A, right? So we will just see you have a let's say something with what's the standard coordinate system doing to A. I think we will all be very clear on what standard coordinate system will be doing to A. It will doing nothing to A, right? This will be equal to this. Nothing is happening. So now suppose we have a minus 1, 0, 0, minus 1. What does this matrix do to 1, 2? Okay. So we will just see what is it actually doing. 1 into minus 1 so it becomes minus 1 and 0 it becomes minus 2. So we'll see. It is just what you tell. It is just giving a negative to this. So in vector form, let's see how this turns about. First, let's plot the directions, right? Let's see what are these directions. Normal coordinate system has these directions, right? And what is the this coordinate system? Minus 1, 0. I'll just go two dimensional. I think, yeah, we have represented it two dimensional. We'll go to two dimensional. So yeah, so he have a vector here, here, vector here. So these two vectors, see, I'm calling it A and B, right? This is standard vectors. These are doing nothing to A that I told. And now minus 1, this vector, let's call it L and M. Okay, this one we'll call it L and M. So L is nothing but this and this, right? So if you travel whatever you are traveling through A and B, if you travel through L and M, where will you reach? You will always reach in a reflection across y equal to minus x, this axis. That is, you're just phase shifting it by 180 degree. Any point can be phase shifted by the matrix, let's say uh, minus 1, 0, 0, minus 1, right? That is what you're doing, right? That you're always from the vector perspective. What this vectors, what did I do? I did 180 degree shift. So any point with respects to this will be 180 degree shifted by this. We are not changing the magnitude. We are just changing the shifting axis. So this, what you tell now very intuitively, this since we did 180, can I think most probably you will be able to tell right now. What should I do? I want to just shift every point by 45 degree. What do I do? Or 90 degree. Let's go with the easy one. 90 degree. It's very quite very easy. 90 degree. What can we do? Very easy. You know this coordinate system. What is 90 degree shifted version of this? This should come here and this should be like, what do you tell? This thing. What is the coordinate system of this one? X-axis is like this is minus 1, 0, right? So minus 1, 0, and this is 0, 1. That's just like that. So this matrix, if you multiply by any vector, it will shift it by 90 degree. That's all. Any vector you have, that vector will be shifted by 90 degree using this one, right? So you can play around with this with any angle. You want to scale a particular axis, then you give a value here, right? You can do like it is up to you. It is the imagination is up to you. You can do whatever with the vectors. You can change the some things which we can do like that. I can just tell you, you can change the face of a vector by defining the what you tell the with respect to the standard coordinate system. You know the vectors of the standard coordinate system, and whatever vectors you define, how it is related to the standard vectors, that it will transform all points in space from the standard dimension. Whatever space is there, it will shift that space by a phase. Phase shift is understood. What you tell, each dimension, if you want to scale, you can just give a here. So dimension scaling is understood, right? Overall scaling, you can do anything you can do. Yeah, like, so that is what basically matrix transformations translate to in vector dimensions, right? So now, since I told you, right, this, if you see these matrices as vectors, they can actually change the phase, the magnitude, a lot of things, right? That is one application of what do you do when you consider vectors as matrices as vectors. Sorry. So in that aspect, let me ask you something else. What else can these, what you tell in that aspect? We get something very interesting, that we can always define a, what you tell, a system. Okay, a system will have, let's say, uh, see, you have a sine omega t, right? In signals and systems, you will be always seeing that this will be, let's say, what you tell. Suppose you have some sine wave. Let's say not that way. You have an input sine wave. Sorry, a very simple system. I'll just show. You have an input sine omega t. When it goes through a system which has a phase of p and magnitude of m, what it does to the, suppose this is uh, a linear LTI system, right? If it is a linear system, then what is a time invariant, linear and time invariant system? What does it have? It will scale, let's say, m sine omega t plus whatever phase is there, right? You need to put it in the phase form. I'm just writing p here. Yeah, but you get the point, right? So that is what this system does. Now we have a way to represent sine omega. If you consider it as a particular vector, you have a way to represent this system in vector algebra by scaling magnitude, this magnitude and phase with respect to origin, right? Now I'm telling you, you have a way to represent that as a matrix also, right? So that is what you tell, that is defining something called a matrix definition of a system, right? In signals and systems, whatever system you're seeing, you can actually represent it by a matrix using this definition, right? Because I told you, what with respect to the standard coordinate system, whatever it is doing to the system, you can code it by just changing those vectors and writing it here as vectors. Okay, so that opens doors to lot of applications of what you tell, ML in system. ML, no, not only ML, what do you tell? First of all, when we talk about this machine learning and concepts, the first thing is you need to get it into a mathematical form, right? Only then you can actually apply all the ML and deep learning. A lot of things you can apply. First, a real world system, you need to actually get it into mathematical form. So this is one idea which can actually help you get it into a matrix form. Once it is in a matrix form, then you can actually apply a lot of calculations. This is very good to get things into matrix form because, uh, as you know, matrix, you know the standard Cramer's rule, a lot of matrix multiplication, the complex what you tell calculations. We have a lot of ways, mathematical tools to carry out all these for us. So those are some of the things. And also when you define a system, right? Earlier I showed what was the, what you tell, what was the, what you tell, the determinant of a matrix, right? That was basically, suppose you had two vectors which defined a matrix. The determinant of the matrix was nothing but the space spanned by these two vectors, provided the scaling factors m times a and b, right? M times a plus b, let's say n times b, m and n being any value, any fraction, it can be a fraction or an integer, provided that root of m square plus n square is less than 1, where all, how much, what is the space you can actually span. In two dimension, it came out to be an area of a parallelogram, right? So this area, right, that was a determinant of the matrix. So space is this, right? So any vectors that come in this space, they are actually the, what you tell, they are actually can be represented by some linear combination of m and b, right? So now this, if this condition is not there, right, m and n is not there, You can write anything in the two-dimensional space. You can actually see you have to it. I mean, A will have at least one perpendicular component to B, right? In that aspect, you can actually reach any point in this two-dimensional space by scaling A and B. Now I'm taking away this restriction, right? M and N, you can put any values, right? That is the space spanned by A and B, correct? So I think it is quite clear, right? Any space spanned by A and B is the linear combination of A and B can get me there, right? So those vectors are all the space spanned by A and B. And if there is any vector in this dimensionality which I cannot reach by the linear combination of A and B, that vectors will be called that vectors in the null space of X, right? So yeah, so that those vectors which are once we get it into a matrix form, right? Uh, we need to give inputs. We'll get an idea what this system can do, and more importantly what the system cannot do. If we know that a vector in the null space, an input vector is going through a what you tell a system of vectors, and it is creating an output vector, right? Now in this case, now if you know the null space of this matrix, right, you know the inputs whom this matrix can actually do nothing to. Not, sorry, the outputs that this matrix cannot give. This system will never give that output, right? Those we will know because that output is in the null space of this matrix, correct? So those are what you call. So that is one advantage we get by by changing the game and taking it into a matrix representation. So these sort of ideas are all it will come up in future when we start actually what you tell getting into the math of ML models, okay, and how they perform. A lot of things we'll actually discuss in future. This is just a basics of some basic mathematics which we can actually help us to understand all these concepts. Okay. Now, having said that, now we have defined a multi-space system. Let's say we'll just get to an example to actually, like you've been actually playing around for quite some time. Let's get to an actual real world example. You have, let's say, two cricket players. Okay, two cricket players are there. Okay, now across, let's say, these players actually across 1 year there are 12 months, right? So these players actually have an average score. Okay, they have a batting average, or people call it, yeah, I hope that is correct. They have their batting average, which is nothing but the total number of runs they score by the number of games they take. Okay, might not be correct. Some people calculate balls or something. We are just defining it. Okay, they have an average, which is the total runs they score by the number of games that they play. So let's say player A and player B, both of them have what you tell some run two averages. Okay, that is for they have averages for 3 years. 1 year they have one average, second year they have an average, third year they have an average. So A has an average here, B have an average here, A has an average here, B has an average here, A has another average for the third year. So B also have another average for the third year. Now my question is, suppose A's average for the first year is what you tell less than B's average. Same way, A's average for the second year is less than B's average for the second year. Third, same thing. A's average for the third year is less than B's average for the third year. So A's average is always less than the individual years, first year, second year, third year. The average of A is less. Okay. Can the overall average of A across the 3 years, okay, let's call it, let's say A O, Can that be greater than the overall average of B over the 3 years? Is it possible? This is one question we need to address here. Intuitively, it doesn't look, because individually each average of A is greater, right? A is lesser, right? How can the overall average be greater? But can you actually prove this statement, or if it is greater or lesser? I mean, can you prove that A's average can be greater, or what condition it can be greater, or is it possible even to be greater? Can you mathematically just prove that? So in this case, this is one application of vector algebra which we can actually uh, just prove. So we'll see how we actually prove that. So we'll see that suppose is we have a, what we are doing is the number of runs A scores. Okay, you have a standard coordinate system. Okay, the number of runs that A score, I'll represent it by a vector with the magnitude along what you tell y-axis, and the number of games that A take, I will represent it by the vector with the magnitude along what you tell x-axis. Okay, so the total average of x, I will represent it. I know that it is a function, right? So I'll just represent it by this way. So what do you tell? It's r by n, right? Runs are coming as the run increases. What you tell, the average increases as the, and okay, this vector is actually 1 by n. Okay, not the number of games, 1 by the number of games. So the number of games increases, what you tell, this average will also, I mean, number of games decreases, this average will increase. Okay, so that is, the representation is quite I think intuitive, right? It is quite clear that one vector will represent the average, right? Now I'm asking you, you have three vectors which are greater than b. Okay, so can the combination of three vectors, suppose b is having each vector b, b1, b2, b3 has to be, what you tell, greater than a. Okay, but what you tell, so this, when you take the resultant of this, it should be greater than a. So let's say b, I am just thinking of situation where, is it possible? So mathematically it is quite exhausting actually if you go for numerical methods to actually solve it. So vector algebra, I'm just giving an intuition how we can get an idea about whether this is possible or not. Suppose, very in a very intuitive manner, imagination manner, I'm just thinking, what if A's magnitude is like, let's say, two games that B played are like this. Okay, what will be the resultant? Resultant will come somewhat like this, right? It's quite evident. The resultant will be, let's say, something like this, right? What I'm trying to tell is that A played, say, the B has scored, what you tell, all the runs in one game only. The other two games, he has actually, it will not be exactly straight, it will be slightly tilted. Okay, I'm telling. Okay, you get it, right? So it is not exactly straight, but slightly tilted. In that manner, what will, yeah, something like this. Okay, this is how individually each one is greater than a, but overall this is how b actually composed his what you tell, averages. So in that manner the overall will be something like this, right? But a, what a did is, individually a scores were like this, that a always took lesser number of games. Okay, in that manner, suppose this is 1 1 and 1, what will be a score? 3, right? Suppose this is 1.1, this is 1.1, and this is 1.1, this is will be what? 2.2, right? 2.2, if you take the root of 2.2 plus 1.1 and you actually square it, how much will it come to actually? Let's say 2 square is 4, 4 plus 1 is 5, root 5. So there's, I mean, I'm not computing the exact value, but it is very evident that this can be less than 3, right? That is quite evident. So let's say, I mean, 2 square plus 2 square, that is 4 plus 1, 5, 2.25. Suppose I'm taking just 2 and 1, okay? And there is a decimal place, right? so that it will slightly increase. But zero point 0.2 and 1 cannot actually if you even if you calculate it cannot be actually contributing to a value which may have zero point 0.7. It can be less than zero point 0.7, right? So I'm not computing it. I'm just intuitively getting that numerical estimate. It will be less than 3. That is the main idea I'm telling here, right? So this definition, if I have this picture in my mind, right? Just give me a second. Yeah. If I have this picture in my mind, I can just tell that this scenario is mathematically possible. So this is another application of vector algebra, right? So a lot of proofs mathematically, what you tell, some places where we find it, what you tell, intuitively difficult to understand. You can use these sort of vector ideas, functions. You map functions to vectors and you represent them as matrices, and you compute them. Right? These ideas can always, like help us in the long run. So there are a few more applications, and more than that, there are a lot of properties of matrix algebra which we need to just have a quick revision of, so that we'll be clear to start. Finishing off the basics of algebra, and we can actually move on to their applications. So we will discuss more applications in the next video lecture. Thanks everyone. So we'll just wind up for today. Thank you.